Okay, welcome to my video on using the 80 column mode on the Color Computer 3 via assembly language. Basically, we're going to show you how to put the machine into 80 column mode, and while we're at it, set a few palette registers, clear the screen, and print some text just to give you an idea of how to use the 80 column mode. And so to begin with, this here basically just states where the program is going to begin. I chose that location because that's where the P-mode screens begin on a disk system, so it's a good spot for it since we're not going to be using the P-mode graphics. And this next section here basically sets the foreground and background color. Clear A essentially loads the A register with the value of 0, storing that into FFB0, stores the color black 0 into palette register 0. Loading A with 3F or 63 in decimal is white, and storing that into FFB8 is the background color, or the the text color essentially. So there's your background color and your text color, and that's it. Basically, just a couple of values. It's like setting palette registers in BASIC, except there's no palette command. You just directly access the correct registers, and FFB0 through FFBF are the palette registers. And then this next section here is what actually kicks the machine into with 80. And so by loading the value of 7E into FF90, so load A with 7E, store A into FF90, that essentially puts it in Cocoa 3 mode. It does some other things too in that register. Right here is what FF90 does. And I used the Lawrence T. Polt books on color computer assembly language programming and the color computer assembly language programming for the Color Computer 3. And there's some other things going on here, but the main graphical thing to note is that bit 7 cannot be set because when it's not set, you're in Cocoa 3 mode, and we can use high resolution displays and text modes. Loading A with 7E and then storing that into FF90 sets us up so that we can use the high resolution modes. And then the video mode register FF98, we take the value of 7B and load that into FF98, and the value of 1F into FF99 sets the resolution. And by examining the video mode register and the video resolution register here, explains where what these values stand for. And so that's this short amount of code. We'll just put it in 80 column. And then the next section here, we need to, the high resolution text mode on the Cocoa 3, when you type with 80, is at 6C000, which we cannot access this memory location using the 6809. It just doesn't have the capability to reach and address that big. And so what we need to do is we need to map it into an area that we can address. For example, memory location 4000. And memory location 4000 is controlled by the MMU register FFA2. So if we take a quick look here, here's the MMU registers FFA0 through FFA7, and then you have a second set at FFA8 through FFAF, and you can switch back and forth. So for example, you can set up the graphics screen in FFA A, B, C, and D, and then you can be using the computer over here, and then when you want to access the graphics, you can switch over here, and just these 4 registers will change. A0 and A1, A8 and A9, and AE and AF, and A6 and A7 can contain the same exact values. So only the middle 4, for example, for like graphics, high-res graphics and such. But what we're interested in is mapping the high-resolution text display into a range, some range here that we can get to on the 6809. And so I'm choosing memory location 4000 through 5FFF. That's an 8K range that's controlled by MMU register FFA2. So depending on what value is in FFA2, that will determine what part of the 512K map is active in that range. And so to figure out what you need to do to get into those ranges, here, let me go over here. Essentially, let's see here. Okay, so here's the section on mapping right here. Essentially, like I said, FFA2 represents this memory range. So the Color Computer 3 uses 6C000 for the high resolution text screen. So since the Color Computer uses that, why don't we? So if we take 6C000 and divide that by 2000 hex, or divide it by 8K, because there are 8K chunks in the MMU. So if we divide that by 2000, that gives us a value of 36 hex. And that's what we get here. So by punching the value 36 hex into FFA2, that will map this range that we cannot get to into a range that we can get to. So poking into memory location 4000 hex will actually go into 6000 hex. 4001 will go into 6C001, and so on and so forth. And so that's essentially what's going on here. We're loading the value of 36 hex into FFA2. That maps 6C000 into memory location 4000. Then the next section here determines the offset. We need to point the gimme chip to 6C000, so you're actually viewing the, so the display is looking at that memory location. So we can only feed 16 bits to the video display offset, but the display offset is 19 bits because 512K requires 19 bits. And so since you can only feed 16K, or I'm sorry, 64K or 16 bits into the video display offset, it just assumes the last 3 bits to be 0. So you're jumping at 8-byte chunks basically. So if you take 6C000 and divide it by 8, it gives us a value of D800, and that's what's going on here. We're loading A with D8, storing it in the FF9D, loading A with 0, and storing it in the FF9E. So we're storing D800 into the offset register. So this actually makes the display look at 6C000, because you can adjust and set the display, make the display look at any portion of the computer as long as it's an 8-byte boundary. So 0, 8, 16, 24, 32, etc. And simply dividing, 6C, dividing the location that you want by 8 gives you the value that you need to punch into the video offset registers at D8 or FF9D and FF9E. And so that makes the video display, this makes it so that we can modify the display, and this points the viewer essentially to that location. And so basically after that, we need to clear the screen. That's what this does. The A and B register can be combined into what's called the D register. And so what we're doing here is loading the A register with 20 hex, which is 32, which is a space in the high-res text mode at least. And then we're loading B with 0, which is for the attribute byte, because we need, the way the video display, the high-res display works, is the first byte is the character, the next byte is the attribute, which determines foreground and background color, whether or not it's blinking or underlined. And so we just want that to be 0 for the time being. And then we're loading X with 4000 because that's essentially the beginning of the display now, based on the mapping we did earlier when we divided 6C000 by 8K and punched that value into FFA2. So now when we access memory location 4000, we're actually accessing 6C000. And so a space into A and a 0 into B, and then we're loading X with the beginning of the video display essentially, and then we're storing D, because A and B add up to D, we're storing D into the X register. So memory location 4000 is receiving the 20 or 20 hex, and 4001 is receiving the 0, and then store D comma X plus plus, that means store the D register into X, so 2000 goes into 4000 and 4001. And then we're incrementing the X register by 2. That's what the plus plus does for us. Then we're checking for the end of the screen, compare X to 4F00, and then branch, if not equal, back to this loop here. And so it'll continue to loop until the screen is clear. This is basically how any CLS routine works. It's taking a value and putting it in the video display and iterating until it fills the whole screen. It's just in this case we're punching in a space and we're loading the attribute value with the value as well. So once that loop finishes, it falls through down to here. This is our text loop. We're setting the X register to point to the beginning of this text down here. You'll see it's labeled text 1. This labeled text 1. So load X with this winds up loading the X register with whatever memory location this compiles to. Right now it's not compiled, so it doesn't know at this point. But when you assemble, that's what the assembling process does. It determines that, and it'll actually say load X with, and then this will be replaced with whatever memory location this T is stored in. And then we're loading Y with the beginning of the display, and we're loading B with 36 hex, which is 36 hex is 54 decimal, and there's 54 characters in this thing here. So this is our counter essentially. So X points to where the text is in memory, Y points to 4000, or where we're going to be putting the text. B is our counter, and then we start our loop here. We load the A register with the value that's in the X register, or in the memory location pointed to by the X register, and then incrementing X, and we're storing it into the Y register, in other words 4000, and we're incrementing X by 1 to point to the H, and incrementing Y by 2 to skip over the attribute byte. And then we decrement the B counter and branch, if not equal to 0, back to T loop. And so it just keeps fetching the next character and storing it onto the display here. Or I'm sorry, storing it here and incrementing X and Y accordingly until it's done. Once it finishes printing the text on the screen, loop, jump, loop, that's like line 100, go to line 100. And then our text, and then our end statement. So that's the program. So let's see it in action here. The whole, like 1 or 2 milliseconds it takes to to execute. And so when I execute this program, it should jump into 80 column mode. The background should be black, the foreground should be white. It should clear the screen and display the text, which should happen too fast to really see. And so there you go. And so all that just to get into the 80 column mode, change a few palettes, clear the screen, and display some text. Okay, let me get out of here. And so just to show how I get here, 80. I generally, when I want to do stuff in assembly language that I'm not really sure how to do, a lot of times I'll use BASIC to kind of test my theories, and if they're correct, then I'll go into machine language and do it. This is kind of a pain to run the editor assembler, get it loaded up, load your project, code, assemble your code, save your source code out, assemble your source code, exit, and then test the program. So basically, this program here does the same thing. Let's see here. So let me just edit 100 and run that line out and edit line 10. And let's change it to a character, like 65 is the letter A. So basically, running this program is doing essentially what I was doing in machine language, loading FF90 with 7E, FF98 with 7B, FF99 with 1F, FFA2 with 3.6 to set the MMU so we can access the high-res display, FF9D with D8, FF9E with 0 to move the video offset to where the high-res screen is, and then a for next loop at memory location 4000 through 4F00, step 2, because we got to jump over that attribute byte, and we're poking the memory location with the value, in this case, the letter Y, or the number that's in Y, which we set to 65. So when I run this program, the display should fill with the letter A. And then, let's see. And then it'll make a sound, which will let me know it's over with. And then what I'm doing after that is like poking a random value into the attribute byte. See, we're starting at 4001 instead of 400. Step 2, so we step over the characters this time. So the screen should start filling with the letter A. And so here, let's do it this way. From the 32 column mode. Now, if you look, and oh, I didn't do the palettes here either, so let's do this. Oops. This is the same thing I was doing in the assembly language program, loading FFB0 as 0, FFB8 was 63. So as you can see, if you look at the listing of this program, there's no with 80 statement, there's no palette commands, and and there's no attribute command either. So if I go into 32 column mode and run the program, it goes into 80 column mode. It sets the background to black, the foreground to white, and it begins filling the screen with the letter A. I could just as easily be filling the screen with the letter or the space. And you can see the text from when I was in with 80 mode, so you can see I'm pointed to the same spot that BASIC pointed it to. And so here we are at the end of the screen. And when I press a key, it will begin randomly punching random values into the attribute memory locations, just to show you. So, okay, so the foreground and background are both red. So you're not going to see any characters at this point. Okay, it's going to happen again. So foreground and background are both black. And I don't know what's happening with underline or blank at this point. So there we go. So the background is blue, the foreground is black, and blink and underline are both off. Okay, so blink is on and the background changed to red from blue. And now blink is off and underline is on. So as you can see, I'm not using the attribute command at all, but I'm just directly manipulating the values in the attribute byte, which is, it's right next to where the character is stored. Character, attribute, for the whole screen. And on it will go. And so there we go. I hope you learned a thing or two. If you have any questions, feel free to comment below or reach out to me on Facebook. And, like, subscribe, and all that silly stuff. Thanks for watching.